We're going to be talking today about significant figures. So this just means that the number that you report in a calculation or in a measurement made in the lab needs to reflect the accuracy and precision of the original measurement that was made. So significant figures, which we also call sig figs or SF if I'm abbreviating it on a paper or a lab data sheet or something, they reflect the precision of the original measurement. Okay. And so measurement was made at some point in the lab, either by a person or by an instrument. And the instruments are designed to provide the correct number of significant figures, or if you are making a measurement using an instrument, you need to know how many points to add, how many numbers to add. We're going to talk about that. Reported measurements have all of the certain digits, plus there is one uncertain digit which is estimated that is placed at the end. There is always only one uncertain digit provided. The precision and therefore significant figures will vary with the measuring device, and any calculations you do must reflect the precision and accuracy of the number that you were originally given in the problem. So here we have a thermometer, and on this thermometer I think that we would all agree that if we were going to record all the certain digits, then this temperature is somewhere between, so if you look at the graduations, right, and then the red goes up to somewhere between 32 and 33, right? So you see that the numbers provided are 30 and 35, which means that each of the graduations or the lines that are on there are for every 1 degree, which is kind of a typical thermometer. So certainly we would all agree that the first digit in my measurement would be a 30, and the second number in my measurement would be a 2. So it's 32 point something. Now it's that last uncertain digit that we're going to argue about. I am certain that this temperature is between 32 and 33 degrees, because that's a 31, that's a 32, that's a 33. Now, where it occurs, we would probably argue, right? That last digit, I don't know, one uncertain digit, we need to put one uncertain digit on here. It's about a third of the way up, so we could certainly make a good argument that it's about 32.3 degrees Celsius. Now, some of you guys might say it's 32.2, some of you might say it's 32.4. That's fine. The 30 and the 2, we agree on those. That 3, we might have to arm wrestle over that last one, okay? We will argue over this one. That's the whole point of the measurement, okay? The one uncertain digit is the one you're going to argue about. But there's only one that you're going to argue about. You're not going to argue about it anymore, okay? So now we need to talk about whether or not a number that you're given, how many significant digits are in that number. So there are rules for whether or not a digit is significant or not, depending on whether or not it's 0 or non-zero. So let's talk about the different kinds of numbers you might see. We'll start with non-zero digits. Non-zero digits like 1, 2, 3, any digit that's not a 0, they are always significant. Zeros are a little more confusing because it depends on where they are placed in the number. Leading zeros are zeros that are to the left of the first non-zero digit. So for example, the number 0.1 has one leading zero. Leading zeros are considered placeholders. And so because they simply hold the place value of the digit that is given there, they are considered not significant. Trapped zeros are zeros that are between non-zero digits. They are trapped. So for example, 101 has a trapped 0 in the middle. Trapped zeros are always significant. So non-zero digits are, for example, 1, 2, 3, 4, 5, anything that's not a 0. The number that's given there in the example for leading zeros is 0.0004. There are 4 leading zeros, none of which are significant. That number that's given, 0.004, has only one significant digit, just the 4. So these zeros are all not significant. That 4 is the only significant one. trapped zeros, that zero in the middle there of 405 is significant. So the number 405 has 3 significant digits. Trailing zeros are a little bit ambiguous because it depends on whether or not there is a decimal point. So trailing zero is a zero to the right of the last non-zero. So for example, the number 100 has 2 trailing zeros. If there is a decimal point in the number, then that means that all trailing zeros are significant. If there is not a decimal point, then those zeros can be construed 2 different ways. If there's no decimal point, they can either be considered not significant, so the number 100 with no decimal point would be considered to have 1 significant figure. However, there are some textbooks that consider having the lack of a decimal point as an ambiguous number of significant digits. And so that is generally the way I like to describe trailing zeros with no decimal point, is that it's generally not a good idea to give a number like that. You know, when you say I walked 1,000 miles to see you, you probably didn't walk exactly 1,000 miles, but maybe you know, your number's accurate to the nearest 10 miles or the nearest 100 miles. You know, if you said I'm going to give you $1,000 for your car, that's probably a pretty crappy car, but you're probably going to get exactly $1,000, right? It's not accurate to the nearest $100. You're probably going to get 1,000, right? So that one's accurate to the nearest $1. So generally it's a bad idea to have ambiguous sig figs when you report a number. So let's do some examples here. How many significant figures do each of the following measurements have? So we'll start with A. Let's look at this number. So we have 0.00101. Now those first 3 zeros are leading zeros. They are not significant. That middle one is significant because it's trapped. So that means that I see 3 significant digits in A, right? Now let's look at B. We have 4.500 times 10 to the minus 3. Now that 10 to the minus 3, that doesn't really matter. That's just scientific notation. But those are trailing zeros to the right of the decimal, and there is a decimal, which means they are significant. So that number has 4 significant digits. So because the decimal point is present, the 2 trailing zeros are significant. Now one way to remember that is that if somebody went to all the effort to add those extra zeros, it doesn't change the value of the number, but it does reflect a higher level of precision and accuracy, which means that they must be important for some reason, otherwise that person wouldn't have gone to all the extra effort to put them on there, right? So B has 4 significant digits. Now let's look at C. C is 1100. Those first 2 are non-zeros, so they're definitely significant. Those last 2 are a little ambiguous, and so you might be wondering, So some textbooks would tell you that that has 2, just the 2 non-zeros, and other textbooks would say you should say that's an ambiguous number. I would prefer that you say that that's an ambiguous number because I don't want people writing numbers that are that ambiguous. You have to be very clear about what you're writing, and we'll talk about how you would be very clear in a few minutes. Now, let's look at D, 100 centimeters in a meter. Now, that is an exact number because it is a conversion. There are exactly 100 centimeters in a meter. Not all conversions are exact, but some of them are. For example, 12 inches in a foot, 3 feet in a yard, 60 seconds in a minute, 60 minutes in an hour. Those are all exact numbers. Time, well, yeah. If we get into days or years, that would be more confusing because of leap years. So we probably won't get confusing like that because there aren't really exactly 365 days in a year. We'll stay away from years. But 100 centimeters in a meter, that is certainly an exact number. Now, E is 0.05020. Those first 2 zeros are not significant, the ones I underline in gray. and all of the remaining 4 digits are significant because one is trapped, and then there is a trailing 0 that is significant because there's a decimal point. So that means that E has 4 significant digits. Now F, a meter stick measures 100.0 centimeters. Now this is a little bit different than D because this is not a conversion. This means I physically took out a meter stick and I measured it in centimeters, and it's not an infinite number of significant figures. It has 4 significant figures because all 3 of the trailing zeros are significant because of the decimal, and the first one is a non-zero, so it's certainly significant. Okay, so next we're going to do a little bit of rounding just to make sure everybody knows how to do this, because there are some misconceptions on rounding, even though it's something you've been doing for a long time now. So we'll start with the first one, 5.974. We're going to round each of these numbers to 3 sig figs. That means we're rounding to that 7. That's going to be 5.97. That's because 4 will round down because it is less than 5. So 1, 2, 3, and 4 round down. 5.977, the next digit is a 7, so that means it rounds up. 6 and up, round up to the next digit to make it 5.98. Now 5.975, this is going to be 5.98. Now there are 2 different rules for rounding 5. And so the rule for 5, I want to tell you 2 different ways, okay? There are 2 ways to do this. You can either always round up. That's probably the way you learned it in high school, is that you always round 5 up. However, because 5 is in the middle, right, then if you always round 5 up, then you can tend to skew your data a little bit, and that sort of pushes everything to be a little bit higher than it should be. Now that doesn't tend to be a problem unless you have unusual data sets, but there is a second rule for 5, which states that you always round to whatever the even number is. And so if you always round to the even number, then that means that you're going to round up about half the time and you'll round down about half the time. That way you don't skew your data. And so in this case, if we're rounding to the even number, either way we get 5.98, right? Now 5.965 is going to round to 5.96 or 5.97. That's the different example. So 5.96 is if we're rounding to the even number. 5.97 is if we're rounding 5 up. Now the next one, E, 5.9749, rounds to 5.97. A lot of people round that 9, round the 4 up to 5 because of the 9, and then they round the 5 up to, they round the 7 up to 8 because of the 5. But remember, you only look at the very next digit. It's just the 4 that matters, not the 9. So that's going to round to 5.97. 4 always rounds down. Now F is the one that I really want to focus you on because this is a big number. Big numbers are weird. So we have 57,963. That's a big number, and we're going to round it to 3 significant digits. 3 significant digits means we need to round it to that 9. We need to get rid of that 6. 6 rounds up, but that's a 9. So now we have 58,000. Now, I don't know if you know the problem with this number. 58,000, depending on our rules for determining significant digits, that either has 2, which is not what we're trying to do here. We're trying to round to 3, or it's ambiguous. So either way, 58,000 does not have 3 significant digits. Now, when I was in school, I learned to put a line over the least significant digit. People don't tend to do that anymore because I guess that was something they did back in the dark ages. So the easiest way, the only clear-cut way to represent this number with 3 significant digits, anybody know? I don't know. How do I do it? That's 0. It's significant. How do I show that? I don't know. That one's not significant. What do I do? I don't know what to do. Well, we've invented this ingenious little tool called scientific notation. If you write this number in scientific notation, you can write, you always have a decimal point, which means that you can write significant, you can choose which zeros are significant. So that is the way you express this number unambiguously. In this case, you almost have to use scientific notation. There is no other way. Okay, that's the one you're going to forget how to do later. Hopefully, we'll remember. So hooray for scientific notation. If you hated it before, now maybe you can show a little bit of love. Okay, so we've talked about significant figures and why we care about significant figures, why they matter. We've talked about how you would maybe make a measurement and report the appropriate number of significant figures for something like a temperature reading. We'll do more of those measurements in lab throughout the semester. Also, we talked about how you would determine if the number that you're given, if a digit given in that number is significant or not, based on whether or not it is a non-zero or a trailing zero or a leading zero or a trap zero. And finally, we need to talk about the rules that are in place for rounding to the right number of significant digits depending on the mathematical operation that you are performing. There are two rules we'll talk about. One is for multiplication and division. The other is for addition and subtraction. There are different mathematical operations you may perform second semester, but we'll talk about those rules when we get to those next semester. So the rule for multiplication and division is that your answer cannot have more total digits than any of the original numbers that were given in the problem. So let's do an example. We have 13.5 centimeters times 1.0 centimeters, 0.4 centimeter. When I plug that in my calculator, I get 5.4. And when I think about how many significant digits I need to round to, I need to first look and see how many are in each number. So 13.5 has 3 sig figs, 1.0 has 2, and 0.4 has just 1. So that means that my final answer should only have 1. So that means I need to round it from 5.4 cubic centimeters to 5 cubic centimeters. The second example shown here, 2.578 grams, and we're going to divide that by 3 cubic centimeters. Now we're assuming that that 3 cubic centimeters is a measurement. It's just kind of a very inaccurate and precise measurement with only 1 sig fig. So when we do calculation, we get 0.8593333 forever. And that means because the top number has 4 sig figs and the bottom number has 1, I need to round my answer to 1 significant figure. Based on my rounding rules, that means that I either have 0.8 or 0.9 gram per cubic centimeter as my answer. Finally, we have the same calculation shown here at the bottom, but it's a little bit different because instead of a measurement of 3 cubic centimeters, we have a conversion factor, which is 3 feet in 1 yard. That is an exact measurement. There are exactly 3 feet in 1 yard, which means that that conversion factor, that number 3, has an infinite number of significant figures, which means that it will not limit your answer. So the number on top has 4 sig figs, which means that your answer that you round to in the end should have 4 sig figs, which means you have 0.8593 yards is your answer. Now our second rule is addition and subtraction. And for this rule, this one states that your answer cannot have more digits after the decimal place than any of the original numbers. Now that's the way a lot of books state it. I think it's more digits after the decimal place or before the decimal place. Some numbers don't have a decimal. And so I think it's wise to keep track of the place in a number. So if we just put in a big number here, 4,321.5678. Now, in this case, I want to make sure everybody remembers what the places mean. Of course, the 1 is in the ones place, that 2 is in the tenths place, the 3 is in the hundreds place, and the 4 is in the thousands place. And if you move to the right of the decimal, the 5 is in the tenths place, the 6 is in the hundredths place, the 7 is in the thousandths place, and the digit 8 is in the 10,000ths place. So when I think about rounding sig figs for addition and subtraction, I just simply think of the place. You know, is it the hundreds place? Is it the tenths place? And I round to that place. So we're going to do some calculations, and I think that will clarify everything. So we're going to do some calculations. The first two are addition, the third one is multiplication, and the last one is a combination of subtraction and division. And that last one's going to be the one that confuses you. The last one is going to be the one that you're going to miss on the quiz unless you really pay attention. let's do the first one. So we're going to add those two numbers together on our calculator. By the way, you really do need to get the right answer in order to get these right. I can't grade it if you get the answer wrong. So please make sure you plug those numbers into your calculator correctly. Please use your calculator. I don't know why you wouldn't use your calculator when it's available to you. So here's the number I get from my calculator. And of course I know I have to round that. So I'm going to look at my first number. The first number appears to be accurate to 1 digit after the decimal, which is the tenths place. My second number is accurate to 4 digits after the decimal, which is the 10,000ths place. That means I need to round my answer that I'm giving to the tenths place, because that is the less accurate of those two, which means I'm going to round it to that 6. The 7 needs to round up, which means I need to round it to 14,533.7 centimeters. Now let's move on. This second problem, the issue here is that these numbers are given in scientific notation. So that first number, 1.2 times 10 to the third, is actually 1200, which is a very inaccurate, imprecise number because it's only accurate to the nearest 100 seconds. And that second number is actually quite accurate, very small, teeny tiny number, teeny tiny time that I'm adding to 1200 seconds. So when I add them together, first I get this. This is what my calculator spits out. But when I round this, the problem is that this first number is so inaccurate and imprecise that the second number, and the second number is so small that it doesn't really significantly add any time. Okay, this would be like if you were recording how, the age of something in that's accurate to every 1,000 years, and then you added in, a second. It doesn't make any difference, right? This would be like if you measured the change in mass from you eating a hamburger, and you went and tried to measure the difference in mass using a scale on the interstate that measures semi-weights, right? So it doesn't make any difference. So that means that when we round this number, this second number doesn't really make a difference at all. So when we round it, we actually have to round it back down to the original number, which is just that 2, 1.2 times 10 to the third. So this is saying that a really small number, really small time, does not in any way impact a larger, imprecise number. I know that's going to bother some of you, but that's just the way it is. Now we have a multiplication problem. 4.55 times 6.0 gives me 27.3. The first number has 3 sig figs. The second number has 2, which means I need to round it to 2, which is a 27. That one shouldn't be too shocking. This last one you have to do in two steps. Okay, so you're going to do the parentheses first. Remember order of operations. If you don't do it right, then I can't give you the right answer. Okay, the math actually has to be correct. So step 1 is to do that subtraction, which gives you 0.06 grams. And then you're going to divide that 0.06 grams by 4.57 milliliters. And so the first step is the addition subtraction rule. And it says that my answer is accurate to the hundredths place. This is my answer when I plug it into my calculator. And we're going to do the sig figs in steps 2. Okay, so the answer to the numerator is accurate to the hundredths place. And then the last part means I'm going to take the 1 sig fig in the numerator and I'm going to divide that by a number that has 3 sig figs in the denominator, which means my answer in the end should only have 1 significant figure, which I know that's going to bother you, but that's the way it's supposed to be. So we have 0.01 gram per mil is our answer.